Okay. Now, number 20 also addresses part of what you need to know for number 19, graphing your functions. Number 20 is solve a given rational or polynomial inequality. And I say here that the sign of any rational function, and of course that includes, what I'm saying includes polynomials, the signs change only at zeros of the numerator or the denominator. Now, if you don't have a denominator, then you just have the numerator, and it's a polynomial. That's also really important for graphing, okay, because this partitions the x-axis into intervals where the sign doesn't change. That's the bottom line. Now, how that's applied in detail, well, check the videos. Maybe I'll do some subsequent videos that explain that, but we have videos that address this pretty thoroughly. Number 21, given a function, determine if it's one-to-one, and if so, find its inverse. Okay? To determine whether the function is one-to-one, you got the equation y equals f of x, whatever f of x is. 2 to the x plus 5, x squared minus 17x plus 3, whatever. Solve that for x. So you're going to get x in terms of y. Okay, so you just keep rearranging it until you got x by itself on one side. What do you have? If there's only one solution for every x, then the function is one-to-one. Okay. If it's one-to-one, then all you have to do is switch x and y, and you've got your inverse function. Now, if you've already solved it for x, you got x equals something and something with y's in it and so forth. Just make that x a y, make all the y's x's, and you've got your inverse function. You can also, and we'll address this elsewhere, but you can also restrict the domain of f of x, if it isn't one-to-one, to an interval where it is one-to-one, and do the inverse on that interval. Then if you have a table, because I didn't necessarily say in number 21 that you've got the function given as an equation, if you've got the table for the function, you can check and see if the table is single valued, if every x value has a unique y value. In other words, if y values don't repeat for two different x values. And we understand that, so reverse the table to see if it's single valued. Okay, for number 22, 23, and 25, you can see number 4 for 22, you can see number 21 for 23, you can see number 5 for 25, they're addressing basically the same thing. Okay, for 26, or you graph the equation of exponential function dot 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 by shifting stretching transformations. It's for example. Well, you have to put the function as you're given into the form a f of x minus h plus k. Now often for an exponential function it'll already be in that form. For example, 3e to the x plus 7 plus 2. Okay? If f of x equals e to the x, then this function is in this form. How? Well, you got, instead of e to the x, you got e to the x plus 7, which means you've replaced x by x plus 7. Well, this says replace x by x minus h. If h is negative 7, x minus h is x plus 7, and you will have replaced x by x plus 7. This means that h is negative 7, so it's shifted 7 units in the horizontal direction. Okay? A is whatever's in front of your f of x minus h, that's 3. So the thing, before you do any shifting, you probably ought to do all the stretches and compressions. You stretch it by factor 3. Okay, then if you want, you can go ahead and shift it negative 7, and then you're going to also shift it 2 units up because you're adding 2 to the value of the function. So that's an example of this sort of thing. You have to know what this form means because it'll be referenced on various problems that could occur. Okay. Okay, so you're wanting to graph a logarithmic function and then a transformation of that logarithmic function, starting with a graph of the corresponding exponential function. And if the logarithmic function is y to the base b of x, which is the premise here, then the exponential function is y equals b to the x. Okay? You start with y equals b to the x, you reverse the columns, and you have now a table that represents y equals log base b of x. Okay? Then you have the transformation. You have some number a, some number h, some number k that fits this form for your logarithmic function, and you transform the function, transform the graph by the appropriate shifts and stretches. To convert an exponential equation to a logarithmic equation or vice versa, well, if it's an exponential function, you want to put it into the form b to the whatever equals q. And whatever can be some expression involving, let's say, x. And you want to solve for x, but it's up here in the exponent and you can't get to it. Well, if that's the case, you convert this to logarithmic form. Okay, so b to the a equals c is equivalent to log base b of c equals a. So this is equivalent to log base b of q equals whatever. Now your x is someplace where you can operate on it. So that's one way of doing it. And of course, if you have log to the base b of some other whatever equals some other q, and you want the whatever contains the variable you're trying to solve for, then you can, that variable's all tied up within the log. You can't get to it. You change it to exponential form, which would be b to the q equals whatever. In other words, we use the fact that log b whatever equals q is equivalent to b to the a equals c, where a would of course be your q and c would be your whatever. So and this is, people didn't have much trouble doing this in class. It's, you got a very simple set of rules that allow you to make these conversions. And those conversions allow you to solve exponential and logarithmic equations. Again, we're not going through the details of the process here. We're just referencing them so you're aware of them. And so you know what the basic premises are before you start getting lost in the details. Knowing the basic premises, you can then work through a number of examples and develop what the necessary understanding. 29, convert logarithms of powers, quotients, etc. To logs of single quantities. You have these three laws of logarithms. Log of AB is log of A plus log of B. Log of A to a power is the power times the log of A. And kind of redundant with this one and this one, because these two could be combined to give you this one. Log of A over B equals log of A minus log of B. Okay? Using those basic rules, you can do what we say in number 29, which is convert logarithms of powers, quotients. Yeah, I said power, quotients, and powers. It should have been power, quotients, and products, but we see how that works. And again, this is something people pick up pretty quickly, as long as you've done enough practice that you remember these procedures and don't start doing things like log of A plus B equals log of A times B, or get the plus in here, because you can't do anything if you got a plus in here. And get that confused, you're lost. You got to know the rules. And preferably you got to know the rules because you understand them in terms of what you do with the graphs and reverse tables and all that stuff. That's a kind of a tall order for most people at this stage. So at this stage, if you just know the rules and don't make a mistake, it's not difficult to do. Okay, number 30. Solve a given exponential or logarithmic equation. And I've already addressed that when I talked about number 28. Just use number 28 where x is part of the whatever. If you understand what I just said about 28, that's pretty much it. Now, number 31, you want to solve a system of two equations, two unknowns by any of four methods. And actually, I never listed elimination, which is the method people usually start with when they solve simultaneous equations. Now, my pictures just indicate graph the things. You get two straight lines. If they're simultaneous linear equations, you get two lines. They cross at some point, and the coordinates of that point are your solution for x and y. Or you can write it in the form ax vector equals b vector, where x vector would be like xy, and the b vector would just be a column of two numbers. And we've been doing that for a couple of weeks. Everybody should be real adept at that. And then use A inverse. Apply the inverse matrix to both sides. And we've got the rule. We've been over that at least twice. Writing down the rule, using the rule for doing the inverse of a 2x2 matrix. And we're only doing two equations and two unknowns. If you get into bigger matrices, you have to slightly expand your repertoire of tricks in order to do the inverse matrix. Everything else kind of goes along the same. Now, there is reduce the augmented matrix. And I'll just mention, if you got three or more equations and three or more unknowns, equal number of unknowns and equations, you get the inverse by doing a matrix reduction on a certain other type of augmented matrix. And that other type is, we have the identity matrix on this side and your coefficient matrix on this side. And you reduce the whole thing like this, but on the other side, you'll have two columns of asterisks, and whatever goes into those asterisks would be your inverse matrix. Actually, you'd have three columns, which is 3 by 3. Anyhow, that's for the future. You don't have to worry about that. You do have to be able to do that for two equations and two unknowns. And then, of course, there's elimination, where you add a multiple of one equation to a multiple of the other and eliminate one of the variables. And that's pretty much equivalent to what you do with row reduction, but in row reduction, you have a very clear sequence of events. You get a 1 here, you get a 0 here, then you get a 1 here, then you get a 0 here, and now you've got your solution. And if that doesn't work, then you think about what this second equation tells you. Does it tell you that you have solutions or you don't? And number 32 is just multiplying matrices. If you know how to multiply a row by a column, then it's easy to multiply matrices, and all you have to do is practice it a little bit. And you multiply each row by each column. Row of the one on the left, every row of the one on the left, by every column of the matrix on the right, and you get a number for each row times each column, and you put the resulting number for each row and column into the corresponding row and column of the product. And that's something people are doing okay, but I do recommend just a little more practice to be sure that you really have it down, and then you end up with an easy problem, okay?